Okay, so last lecture we stopped at finding out which Hamiltonian gives me the Hartree-Fock function as an eigenstate. And we saw that it is the sum of the Fock operators of all the electrons. But the eigenvalue that corresponds to this approximate Hamiltonian was not the Hartree-Fock energy that we derived from the variation principle. So last class I tried to explain that, but in a hurry I was not able to do it properly. So today we will start from there and try to understand why we get these two different energies. Okay. So let's say my psi naught is the Hartree-Fock wave function. Then certainly psi naught is not an eigenstate for the full Hamiltonian. So this is the full Hamiltonian, and psi naught is an approximate solution. So certainly it is not an eigenstate of the full Hamiltonian. However, it is an eigenstate of some approximate Hamiltonian with some approximate energy E0. So this is an approximate Hamiltonian. This is some approximate energy. And this is an approximate wave function. However, and when we found out that the H0 that satisfies this equation is sum over I of Fi. Okay, and E0 is an expectation value of H0. However, remember that the Hartree-Fock energy expression that we obtained from the variational principle is the expectation value of the full Hamiltonian with respect to psi 0. And this has the form this is what n it is this form. On the other hand, E0 is equal to sum over all the orbital energies, and that is sum over A HAA plus sum AB JAB minus KAB. So there is a difference There's a difference in the two energy expressions. So H0 psi 0 is not equal to the Hartree-Fock energy psi 0. So this is a confusing situation. So we obtained an approximate wave function, and we found the Hamiltonian for which the function is an eigenstate, but the eigenvalue that we get is not the energy that my derivation tells me. So the derivation from the variation principle, that is not the eigenvalue. So somehow, using the variational principle to obtain an energy and a wave function is not equivalent to solving an approximate Schrodinger equation. So why is that? We need to understand that carefully. Okay. So let's notice that in both cases, the expectation values that we evaluate are different. So E Hartree-Fock is the expectation value of the full Hamiltonian. E0 is the expectation value of the approximate Hamiltonian with respect to the same approximate wave function. And when we applied the variational principle, we applied it to this, to the expectation value of the full Hamiltonian with respect to a single Slater determinant. We optimized this energy variationally to obtain psi naught. And why did we do this? We used this expression because it came from the Schrodinger equation, which we had assumed to be this. So in order for expectation value expression, we had to start with some Schrodinger equation. But what has happened when we went from here to here? The answer that we get from solving this equation does not satisfy this equation. So this is very confusing indeed. So understand this. Let us look at a simpler example. So the thing is that the operator equation, the Schrodinger equation, is actually a much more stringent equation than the condition on the expectation value. So what has happened is we have integrated out a lot of things from the Schrodinger equation to get the expectation value. So getting a function which satisfies, which integrates to an energy, so that is a much weaker condition that the psi naught needs to satisfy than if the full function had to satisfy the Schrodinger equation. So is this clear to everybody? So on the Schrodinger equation, in the Schrodinger equation, there are functions on either side. So this is a full xyz function. And psi naught has to be such that it satisfies it for every x, y, and z. But the expectation value equation, that is only a number. So psi naught only has to be such that it integrates to a certain value. If this is, I can take a simpler example. So let's say I want to find the shape of a object or the dimensions of an object which satisfies an equation like this. Okay. So here you can simply solve this equation directly. That is analogous to solving the Schrodinger equation directly. And this will immediately tell you, oh no, let me just shift it to the next page. So this is an example. Then this equation immediately tells you that the solution is x equal to a, y equal to b, z equal to c. So what sort of a function is this? This function draws some sort of a cuboid of dimensions a by b by c. Okay. However, if I had told you, so if you integrate this across all the borders of this function, then the volume of the object that you would have got is ABC. But if I told you that you only need to satisfy this equation, that the volume be ABC, then it could be anything. You could find a solution that is a sphere, you could find something that is a cube, you can find something that is a pyramid, you can find a lot of things which just satisfy the solution that B is equal to ABC. But let's say you know a little bit more. Okay. Let's say you know it is a cuboid. If you know it is a cuboid, then one answer, if I know it is a cuboid, then one guess can certainly be a by b by c, a into b into c. But you can have many other things. You can have a by 2 into 2b into c. You can have a by 53 into 2b into 53C by 2. You can have many, many, many solutions. But they all give you a volume ABC. Okay, so here what do I know? I know the form of the exact solution. And from the fact that I know its volume, I'm finding the solutions. But this is still not equivalent to what we have done here. So here we have also approximated the form of the wave function. So the wave function is not necessarily a single determinant, but that is also approximate. So that is sort of equivalent to saying that I have assumed that my shape is, say, a cube. So if it is a cube and I am given a volume V, then I have only one variable in my hand, which is the side of the cube. So the equation that I'm satisfying is d cubed equal to V. And then what I find out is d is V to the power 1/3. Now my volume equation is still satisfied. But d equal to V to the power 1/3 is not a solution to equation 1. But it satisfies equation 2. So this is the situation that is sort of analogous to what we have done for Heartry fork. And when we knew that it was a cuboid and we found various solutions, that would be equivalent to doing a CI or configuration interaction or a full configuration interaction, which we will learn about later. So so are you convinced that solving the Schrodinger equation is not the same as satisfying the expectation value equation? Anyone has a question here? No? Okay. But for Heartry fork, we can do a little bit more. That is, let's look at so we get back to Heartry fork. Let's look at what is the difference in H and H naught at the operator level. So at the operator level, H was a sum of all the 1 electron paths plus the Coulomb interaction, and H naught is sum I Fi, which is equal to sum I Hi plus sum Ij Coulomb operator minus exchange operator. And this is what is called the Heartry fork potential for electron I. So this is called the Heartry fork potential for electron I. So V Heartry fork tells me the field in which electron I moves. This is also something we were talking about last class. Why is it called a self-consistent field equation? So this is the field that in which electron I moves, effective field from the other electrons. So then the difference between H and H naught, we can call that some V operator. That is basically half Ij Rij inverse minus sum I VHF I. So this is a difference. So, and this is what gives you instantaneous correlation. So the difference between having an effective field in which electron I moves and knowing the exact positions of various electrons which respond to each other, so which move with respect to each other. So this is the difference in the Hamiltonian that represents this. And then if we take an expectation value with respect to psi naught, then psi naught H psi naught is E Hartree Fock. Psi naught H naught and that is V psi naught, and that is equal to this. Okay. Uh, of course, you cannot exactly evaluate this because that was my problem in the first place, to evaluate the expectation value of this first term. But we do know what EHF minus E0 is. So psi naught V psi naught is equal to E Hartree Fock minus E0. Let's look at that once more and see what the difference is. So I wrote the two expressions here. So if I do E Hartree Fock minus E0, my one electron part will cancel, and from the two electron part I will get minus half. I will get minus half sum AB JAB minus KAB. And this can also be written in short as AB, AB, if you remember this notation. So this is the balance. If you remember perturbation theory, so this is probably done in your basic quantum mechanics class, but it will also be done again after I finish Hartree Fock. So you can wait a bit if you are confused by what I start with. So in perturbation theory, what do? You split the Hamiltonian into a zeroth order part and a perturbation part. And then when you find out the first order perturbed energy, the expression that you get is psi naught V psi naught. So this is exactly what we have here. So here also we have two parts of the Hamiltonian, the zeroth order part over here and V, which is the perturbation part. And this perturbation is coming from the instantaneous electron correlation. So here you can see H is equal to H0 plus V, and this is the V. And I know now, and I have seen that the difference in my E0 and E Hartree Fock is exactly psi naught V psi naught. So E Hartree Fock is basically E0 plus the first order correction. And in the notation of perturbation theory, I can shift this 0 up, so zeroth order energy plus first order energy. So what has happened? So the Hartree Fock energy that I get from the variational principle is actually not the eigenvalue of the approximate Hamiltonian, but it is the first order corrected energy. So it is better than what you would have got by solving the Schrodinger equation uh, with the approximate Hamiltonian. And this is a characteristic of the variational principle. And this comes back time and again in post-Hartree Fock methods as well. So when you use variational methods to obtain the energy, the energy is better than the wave function, since you're applying the variational principle on the energy. Just think about it a little. It can be a little bit confusing at first. It is still not the exact energy. It is only first order corrected. But it is better than what you would have got by just taking H0 and solving the Schrodinger equation. Is it clear to everybody? Is it clear? Is it clear? So the difference between E0 and Heartry turns out to be exactly the first order correction. So everything is consistent. Okay. Fine. So if it's I think it's probably still a little bit confusing to you. If you have doubts later on, please ask. Okay, because we will shift gear and go to another topic now, and that is the charge density. So recall that we spoke about the Fock operator. So we will talk about the charge density now. Remember that we have said that the Fock matrix, which has elements F mu nu being atomic orbitals, that depends upon the so-called MO coefficient or molecular orbital coefficient or the coefficient matrix for the basis functions. But this can also be transcribed to a dependence on a density matrix P. But I didn't say much about the density matrix then. I just told you that it looks something like C star C. But that's also not quite true. It's actually C star, but that is what I had said, that it is C star C. But where does it come from, and why on earth is it called the charge density? So let's talk about that a little. So let's say we have spatial orbitals, and these spatial orbitals then depend upon only the spatial coordinate r. So what is the probability of any electron? So what is the probability of any electron being between r between r and r plus dr. Note that I am saying any electron. So what is the situation? Let's say we have an atom. This is the nucleus. We have some 1s orbital, 2s orbital. Then we have 2p orbitals, px, py, pz. Okay. And let's say I want to know what is the probability of finding any electron in some volume element dr over here. So there are multiple orbitals which contribute electron density to this volume element dr. So what is the probability of having an electron from spatial orbital psi a at dr? That is mod psi a square into dr. So that is for one orbital. Now, since this is a spatial orbital, you can have 2 electrons in it. So this is 2 times mod psi a squared dr. And since in principle all orbitals can contribute density here, you sum over all orbitals a, n by 2. And this is the total probability of finding any electron between r and r plus dr. Okay. Now from this expression, we define this as the charge density rho r. And rho r is then 2 sum a equal to 1 by n by 1 to n by 2 mod psi a square. This is called the charge density. It is a function which tells me how many electrons are present at a certain point r. So, the most important property of this charge density is when you integrate over all space, what do you get? So every spatial orbital is normalized. So this integral is 1. So you have to, and then when you sum n by 2, 1 to n by 2, n by 2 times, you get n by 2. So the integration of the charge density over all space is the number of electrons. So now let us come back to my Fock matrix. Fc equivalent to Fp. What is P? These are all in the atomic orbital way. This P is also in the atomic orbital. And this is the density matrix. So here we have defined the charge density as a function. It is not yet a matrix. So how will we identify this matrix? Every spatial orbital or molecular orbital is expanded in a atomic orbital basis. Is expanded in a atomic orbital basis. So we put back this expression in the probability. So we put this here. And what do we get? Some new. Then we take out the coefficients and sum over A. So we take out the big sum first, and then we put this together. And we call this an element of the density matrix, P nu mu. Okay, missed the DRs over here. R, DR, DR. So this is now the density matrix in AO basis. So with regard to the charge density, then there are two things. They are related but not the same. You have the charge density function, which is defined with the spatial orbitals or the answers to the Hartree-Fock equation, the molecular orbitals. And you have the AO density matrix, which is the matrix representation of the density function in atomic orbital basis. This goes in as input to the Hartree-Fock equations. So there are two different things. I will go back to the lecture in which we introduced this in the first place, so that I can show you what we had done there. I think it's this one. Yes, so notice what we had done here. So here, we were trying to construct the Fock matrix in atomic orbital basis. So we took the operator and we put the atomic orbital over here, and we obtained the matrix elements. And we noticed that the Coulomb and exchange integral part involved the MO indices, or the molecular orbital indices, or the, yeah, so the answers. And then we expanded these molecular orbitals in the atomic orbital again, and we obtained this C star quantity, which we defined as the density matrix, or atomic orbital density matrix. This is the expression. So it's the same, right? So what we did today, there is only a slight difference here. So here, uh, which is actually a mistake. So notice that since we did it in spatial orbitals, we have included the number 2 in our definition. So here, what should have been the case is 2 would have gone into the definition of P, and this would have changed to 1, and you would have a half here. Okay. I will upload the correct notes. I will replace it on VLearn so that you don't get confused. But if you have already printed it or something, then note this change. So in the definition of the density matrix, the 2 is included. So here, when we use the expression, the 2 will go into P, and you will have 1 minus half over here. So that is a correction from, this is lecture of 5th February. And like I said before, this is done for numerical reasons, because it is much simpler to store and update the density matrix than the coefficients. Because this is because if you keep the coefficient expression, then firstly it is larger, and also you have more operations to do every time you compute the Fock matrix elements, and you have to do this because the Hartree-Fock is an iterative procedure. So at every iteration, the coefficients get updated and the Fock matrix must be recomputed. And this is also the most expensive part of the calculation. So you want to improve it as much as you can. Okay. So let's get back to today.
Ma'am, for that part, I have, I mean, I forgot the reason why thymine set are not orthogonal that thing. Uh,
Why it is not orthogonal? Okay,
the set of
so why?
atomic basis.
Yeah, so the reason is that it is difficult to construct them to be orthogonal. What you do is you have a set of basis functions that are already predefined for various atoms. Okay, so this is like a database, and you in a molecule you have many atoms. So there is no
Oh,
when you create these bases for different atoms, uh, there is no reason why they will be orthogonal. You could have
yes, will
explicitly
they be?
orthogonalized them.
Yes, they will be linearly independent. So, we
Not
linearly independent.
necessarily.
Okay.
So the basis function they are chosen to be linearly independent mostly, but sometimes there is some dependence as well because they're different atoms and the condition or and they are constructed more or less intuitively. Okay, so the basis functions they look like S and P orbitals, like atomic S and P orbitals for every atom. And then when you put them in a molecule, so when they were formed, the functions they didn't know of each other. So your hydrogen can be in a methane, or your hydrogen can be in lithium hydride, or your hydrogen can be in hemoglobin, but they will still have the same functions. So they don't know what the other things are. So there is no guarantee that they will either be linearly independent or orthogonal uh, or orthonormal. The normalization is taken care of because they're individual functions. So that part doesn't depend on the rest. But the orthogonality depends on the rest. And if you don't know what the rest are, you can't ensure it. That is why they are in general not orthogonal. You could have orthogonalized it when you started. Okay. But I will tell you just I have an important call. Just hold on a minute. I will tell you why it is difficult to uh, orthogonalize them before you start. Just 1 minute. হ্যাঁ বলো 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 হ্যাঁ আচ্ছা হ্যাঁ করে দেবো একটু পরে আসছি একটা ক্লাস নিচ্ছি নিয়ে আসছি করে দেবো ঠিক আছে আমি আসছি হ্যাঁ হ্যাঁ ঠিক আছে আমি আসছি আমি একটা ক্লাস নিচ্ছি আমি আসছি yeah uh, and the reason okay so let's get back to this and the reason why we don't orthogonalize before we start is basically computational. It will become more expensive in a way. So so when you're constructing the integral, uh, let's go here. Yeah, so you see, you have these integrals that you have to evaluate over the atomic orbitals, and this is done numerically. Now, if suppose you go over to some sort of orthogonal basis, mu prime, lambda prime, nu prime, sigma prime, then every mu prime will be a linear combination of, in principle, n atomic orbitals, where n is the number of functions in your basis. Okay. And similarly, lambda prime, mu prime, and sigma prime. So, constructing one integral will become n to the power 4 times. It will be equivalent to, to n to the power 4 times the integral. Because the functions that you can integrate are still mu, lambda, nu, sigma. And this mu prime will be a linear combination of all the mu's, lambda prime of like one, the full set. So you have to do a lot of more computations to compute the integral. This will become very expensive. Instead, what you do is you have this x over here, and this x tells you the transformation of the coefficient matrix C, which gives you the coefficients equivalent to an orthonormal set. So implicitly, your basis set does become orthonormal. But you don't actually transform the functions before you construct the integrals. The integrals remain in this, let's say, linearly dependent basis. But you know the transformation which will take you from the linearly dependent basis to the orthonormal basis. You know it. And you use it in the equation. So the equation is still solved as if my basis was orthonormal. Do you understand my point?
Yes, it is.
You understand? So
Yes,
it's a smart
yes.
way of doing. It's a smart way of doing it, actually. So when you choose the functions mu, lambda, nu, sigma, you only have two considerations: that they look as much. Uh, so they one is that you describe the physics well, and the other one is that you represent them in functions which are easily integratable numerically. So that is the only thing you think of when you decide how you will represent your atomic functions. And the linear dependence, you find the transformation matrix and you place it in the suitable places in the equations. You will get it when you learn a little bit more about the basis sets. Maybe then it will become more clear. Okay. So this brings me actually to the end of this class. We only have only 3 minutes left. I had thought of asking you to do exercise 3.12, but since we do not have time to do it in class, you can just do it at home. It is quite simple. It will not take you long. So just do. So do exercise 3.12. Let's say this is homework for tomorrow. It will not take you more than 10 minutes. And we will hopefully finish Heartry theory. So on Friday, I think we will. I'm not sure what I will do actually. Okay, I will not give you a preview. I will tell you tomorrow. Fine. And you are all okay with the assignment too? It's almost on track. Okay, fine, fine. We will talk again tomorrow. So, someone please stop the recording.